So, ladies and gentlemen, thank you very much for inviting me to this workshop. It is my great pleasure to come to Korea, which I visited already several times. It is a wonderful country with wonderful people, and I'm really happy to come here. My today's talk is devoted to a concept which is, synergy of several already existing concepts, and I believe that this concept, which is called fuzzy natural logic, will be a topic of interesting research for some future years. This is outline of my talk. First I will speak about the concept of natural logic itself, then I will present general ideas about concept of fuzzy natural logic, then about main tool, which is higher order fuzzy logic, the technical tool on the basis of which this fuzzy natural logic should be constructed, then few words about part of natural language which already has been modeled, and human reasoning, and also a few conclusions and references. Let me also say I will be speaking about natural language and its semantics, but my idea is not to cover natural language its full wealth, because it is practically impossible. It is topic of research for already several hundred years, and I think that for the next several hundred years it will still continue, because natural language is one of the most complicated structures in space in our universe. Anyway, my idea is to propose the scheme for modeling natural language semantics, and also the way how we could reason using this natural language to make it technical tool for various kinds of applications. In fact, this path has already been started, or it has been initiated many years ago, besides others, by Lotfi Zadeh. Lotfi Zadeh is a great man who inspired research in this topic very much, but what has not been done sufficiently well is mathematical elaboration, and this is the main idea of the concept which I will be speaking today. Concerning concept of natural logic, in 1970 George Lakoff, famous American linguist, published a paper, Linguistics and Natural Logic, and in this paper he presented the following goals. First of all, that this natural logic should be able to express all concepts capable to being expressed in natural language. So natural language is here essential. To characterize all valid inferences that can be made in natural language. So this is connection of natural language and logic itself. And to mesh with adequate linguistic descriptions of all natural languages. So the idea is not to be confined only to one concrete natural language, but to capture the basic principle of the way how people understand each other. I think this is quite natural, because, for example, in this room there are people from various countries having various mother tongues, and still we can understand each other. We are using English as our communication tool, but still this communication tool is not English itself, but our natural language which we know, and which we know from our childhood. So there are some basic principles which can be followed, and also I argue that they can be mathematically modeled. So, in general, which follows from George Lakoff's paper, natural logic should be a collection of terms and rules that come with natural language and that allows us to reason and argue in it. And he also presented very interesting hypothesis. It is very difficult, or practically impossible really, to prove such a hypothesis, but it can be demonstrated, and it will be demonstrated during the development during the years. The natural language employs a relatively small finite number of atomic predicates that take so-called syntaxal complements. It means special extensions, special complementation in natural language, and are related to each other by meaning postulates that do not vary from language to language. This is also very essential. It means that there is only one say, principal natural language, and our natural languages, either Iranian, French, English, Czech, whatever it is are only a system of, say, science of the way how we present our natural language which we have inside. And this, what I'm speaking, natural language which we have inside, is direct reflection of the way how we think. According to philosophical dictionary, if you look at it, you will learn that natural logic already does exist. It is something we have to start with and specify later, and that we may well come to be revised and extended quite seriously. And another item is from the same dictionary, that the natural logic is something to be given in more or less the same way to any able speaker of natural language. Again, the same idea that all people can speak the same way, can understand each other in the same way. And there are considerable number of terms and rules which are usually implicit, simply known to us, and we are using them without explicitly realizing that we are using them, which enable every speaker to argue and reason that every speaker knows and has extensive experience with. So these are essential ideas which stand behind the idea of fuzzy natural logic, about which I will speak. Let me only mention that there are some other people contributing to the concept of natural language. Among them, perhaps you may know the name of Jan van Bentem, very famous logician who is very influential in various areas of logic. I was still speaking about natural language, and one of essential features of semantics of natural language is vagueness, and therefore this is natural bridge to the idea of fuzzy natural logic. In this bridge, let me first mention the concept which is not so much well known, but which in fact was initiated already in 1995 by me. And this is the so-called fuzzy logic in broader sense. Please don't mislead it with Zadek's proclaimed fuzzy logic in wide sense. By fuzzy logic in wide sense, he simply means everything where some fuzzy set concept is used. This is not my idea. My idea of fuzzy logic in broader sense was that it should be, say, extension of mathematical fuzzy logic. And its paradigm was said that to develop a working mathematical model of linguistic semantics, at least some of its parts, and to develop a mathematical model of natural, it means common sense human reasoning. And in general, it should be extension of mathematical fuzzy logic in narrow sense. You may know that this mathematical fuzzy logic has been initiated in 1969 by Joseph Gauguin in his famous paper, The Logic of Inexact Concepts, and then followed by Czech mathematician Jan Pavelka, also including me, and perhaps you may know also the name Peter Hayek, who published his famous book in 1998, and where he also proposed a wide area for research of so-called mathematical fuzzy logic. So, concerning fuzzy natural logic, it requires mathematical model of linguistic semantics, and I argue that mathematical fuzzy logic provides necessary means. What should be followed? First of all, we should follow results of classical linguistics. I think this is without any discussion. And then we should follow also methods of logical analysis and semantics of natural language. The source of inspiration should be so-called Montague grammar. In fact, it is a system of higher order classical logic, so-called type theory, using which Richard Montague in 70s last century proposed the, say, general mathematical framework how to model all natural languages, and not only semantics but also their syntax. And also, what is helpful in this path to fuzzy natural logic is logical analysis of concepts, as has been proposed essentially by logician Pavel Tichy, and then followed by Pavel Materna and some other people. They speak about so-called transparent intentional logic, which is in some sense it is related to the idea of Montague grammar. So in general, fuzzy natural logic should be a result of cooperation with linguists and philosophers. Now about fuzzy natural logic itself, what it can provide. It can provide construction of models of systems and processes on the basis of expert knowledge expressed in genuine natural language. So the idea is simply that expert doesn't use any special formalism. He uses his natural language, and using this he provides his knowledge. And the final idea, or one of essential idea, is to make computer to understand natural logic and to behave accordingly. So all these famous science fiction movies that robot looking like a human comes to you asking you what you wish, and you say him bring me coffee and say some joke, and the robot will laugh and so on. So this is the idea which might at least partly be a result of fuzzy natural logic. Current constituents which stem from this concept of fuzzy logic in broader sense, but can be taken as part of fuzzy natural logic, is the so-called theory of evaluative linguistic expressions, then a theory of fuzzy linguistic if-then rules, and logical inference. We will speak about so-called perception-based logical deduction. Then also theory of intermediate natural language quantifiers and generalized Aristotle syllogisms. And finally, say, formal models of special common sense reasoning cases. Now I will speak about the main technical tool, which is higher order fuzzy logic. So motivation for this is that we can argue and that logical analysis of concepts and natural language, I mean semantics of natural language expressions, requires higher order logic, so-called type theory. This is not my proclaim, it is already argued for more than 100 years by logicians and linguists, and I think we can believe them, that simply classical standard predicate logic is not sufficient for this task, because natural language is really extremely complicated. So we can ask, why should we extend this type theory to fuzzy type theory? First of all, it is a constituent of mathematical fuzzy logic, and we can say that it is now well established with good mathematical properties. And also, and this is one of essential reasons, it suggests possibility how model of vagueness can be included in the developed mathematical models. A few words about fuzzy type theory. First of all, it is a generalization of classical type theory. Classical type theory has been established by Bertrand Russell more than 100 years ago, and then it was developed especially in its formal way, initiated in 40s by Alonzo Church, and then especially in papers by Leon Henkin in 50s. He proved that higher order logic, it means type theory, can be made complete. We speak about so-called generalized Henkin completeness. Also his schoolmates Peter Andrews and also some other people like Per Martin Lev and many other ones. So all of these people contributed to development of classical higher order logic. Since now I will simply speak about type theory or fuzzy type theory, and you could take it as a synonym for higher order logic. Syntax of fuzzy type theory is extended lambda calculus. It is extended in the way that it has more logical axioms, and of course it has many valued semantics. Similarly, as in case of say propositional and first order fuzzy logic, there are more versions of fuzzy type theories. The first version was based on so-called IMTL algebra, involutive MTL algebra, then Lukashevich algebra, and also special algebra developed especially for this fuzzy type theory. This algebra is called EQ algebra. Concerning syntax, because it is type theory, the main concept here is so-called type. You should understand type as a, say, certain index, subscript, or some way how to distinguish objects of various quality, various kinds. It is constructed in a recursive way, and it starts with two so-called elementary types. The first type is truth values, denoted by Greek letter omicron, and objects denoted by epsilon. So these are two kinds of objects with which we treat, and from this we form composed types. These composed types are simply sequences of Greek letters in the notation. And I will explain very early what does it mean. So simply you compose from already composed types, you form more and more complicated types in the way which is classical in logic in general. Then, having the concept of type, we can form the concept of formula. Of course, I have no time to discuss it in detail, but to give you some idea about it. Each formula is assigned a type which is inseparably joined with it. So we use this denotation. So this we speak about formula A of type alpha. If we write formula A of type beta, then it means that these are different formulas. Type is inseparably from it, and formula with its type is this object which is fully defined as itself. This is another formula, and this is also so-called lambda formula. You can also in the literature meet the term lambda term. I don't like this word lambda term. I prefer to speak about formulas. But if you see in the literature the word lambda term, it is the same as I am speaking about formulas. So, first of all, if we have formula of type omicron, that this formula represents truth value, and therefore such formulas are propositions. Very important, essential proposition, it is a formula of type truth value, is fuzzy equality. It simply says that objects of type alpha are equal to some other objects of the same type. And this is essential. If you look at this type beta alpha, then if we have formula of type beta alpha, then its interpretation essentially is a function. It is a function assigning to each object of type alpha some object of type beta. Notice this reverse order, which is useful because it simplifies the way how types can be written. Concerning truth values, as I said, there are several kinds of type theories depending on the chosen structure of truth values. What is essential for fuzzy natural logic, about which I will speak in few minutes, is standard Lukasiewicz MV delta algebra. The MV delta algebra, it is of course very well known, but it has very nice properties, and I can say that it is in some sense the closest non-trivial generalization of classical Boolean algebra. It has all interesting properties of Boolean algebra, and only one essential, which is distributivity of the operations, is left, and gives rise to MV algebra. Let me also mention that MV algebras have been established by C.C. Chang in 50s already. It is quite well-known concept. I think everybody knows this algebra, so I will not speak about it in detail. It is simply lattice endowed with two additional operations, which are usually called Lukasiewicz conjunction, Lukasiewicz implication, and also delta operation. Delta operation is essential in fuzzy type theory because it can somehow extract Boolean structure. It means that it picks up one and puts everything which is lower, I mean every truth value which is lower than 1 to 0. So this is essential operation. Other operations like negation are derived, and what is very important, especially for fuzzy natural logic, is that it has the property of double negation. Concerning logical axioms, I have no time to speak about them in detail, so let me only mention that there are several classes of axioms. 4 fundamental axioms. The most fundamental are these 2 ones. This is the axiom, so-called lambda conversion. Well, it simply says that this formula represents in fact a function. You could read it that every x alpha is assigned some value b beta. So it is a function, and if we say take one specific a alpha and replace it for x alpha, then we obtain the value b beta, and this is here denoted by c beta. And therefore this axiom says that what we do in this process is the same like specifying some concrete formula c beta, where you can read it here, is obtained from this b beta by replacing all 3 occurrences of variable x alpha in it by the formula a alpha. Well, this is a complicated formulation, but this axiom is not so complicated, but very powerful and very important axiom which is used in this fuzzy type theory. There are some other axioms like 2 equivalence axioms, implication, and so on. I will not speak about them in the detail. There is also this predicate axiom. This is standard axiom which is also introduced in classical predicate logic, and very specific axiom, so-called axiom of descriptions. This axiom of descriptions in some sense introduces the operation of defuzzification. So on the level of semantics, if we have such a fuzzy set which is normal, which has one element kernel, or it doesn't need to be one element, simply kernel which is non-empty, then this axiom of description assures the way how we should assign one value which represents the whole fuzzy set. It is the really idea of defuzzification. There are also 2 inference rules. The first rule is so-called Leibniz rule, which you can also read it in a way as equivalence axiom from predicate logic, but it is more general. And also necessitation rule, which allows us to infer from formula, from proposition which is true, proposition which is for sure true. And we have the concept of theory, which is, say, in a standard way. Theory is a set of formulas of type omicron. It means it is a set of propositions. And as usual, we can introduce the concept of probability. And concerning semantics. So semantics is based on the concept of frame. Frame is a system of sets endowed with some fuzzy equality. So on each set of the type alpha, it means set of some specific objects. It can be some very complicated set of functions, and each such set of function is endowed by fuzzy equality, which fulfills these 3 properties. These are quite standard, and generalized transitivity with respect, in our case, to Lukasiewicz conjunction. And also, of course, the corresponding algebra. So in our case, it will be Lukasiewicz MV delta algebra, but this can be some other kinds of algebras. So we can imagine the scheme in this way. Of course, it is infinite structure. We start with structure of truth values endowed with equivalence, then some set of elements, arbitrary elements, having determined in arbitrary way, endowed with some specific fuzzy equality. And from this we construct, first of all, we construct functions over truth values, then we construct functions over elements. So in fact, what are these functions? These are nothing else than fuzzy sets. So this is a set of fuzzy sets endowed with corresponding fuzzy equality. These are simply functions over elements and so on. We continue up to infinity and we obtain this hierarchical structure which is called frame. In this frame we in precise way introduce interpretation, so only to have some idea. In general, interpretation of such formula A beta alpha is some function taken from this set of functions from elements m alpha to m beta. So for example, interpretation of such a formula is simply a truth value. Interpretation of this formula is truth degree of fuzzy equality between element, which is interpretation of this formula A alpha, and element which is interpretation of this formula B alpha. As I said, this is simply fuzzy set, fuzzy relation, function of objects. Of course, fuzzy sets of type 2 and other things like that are very easily expressible in this logic. So what you can see is really very, we have a very powerful tool in which moreover this generalized completeness of Henkin style does hold. This completeness theorem has two versions which are equivalent. So the first equivalent formulation of this theorem is, in fact, as you can see, just classical. A theory of fuzzy type theory is consistent if and only if it has a general model. And equivalent with that is that for every theory of fuzzy type theory and a formula of type proposition, this formula is provable if and only if it is true. It means true in a degree 1. Fuzzy type theory has a lot of interesting properties and really very great explication power, and therefore it is a reasonable tool to be used in development of fuzzy natural logic. Now a few words about natural language. I will not speak about natural language in general, but what is done already and which belongs to this fuzzy natural logic. The first is class of so-called evaluative linguistic expressions, and the second is class of intermediate quantifiers. So, first about evaluative linguistic expressions. Evaluative linguistic expressions, or simply evaluative expressions, are small but extremely important part of natural language, which you may notice yourself that you are using these evaluative expressions in almost every sentence. Simply, these are expressions, these are few examples, there are infinitely many of these examples, which we somehow use to evaluate it, some properties, some values, some characters and so on, rather strong or also intelligent, and many beautiful, ugly, and many other expressions like this belong to the class of evaluative linguistic expressions. They have some structure. And here I will speak only about small subclass pure evaluative expressions which are formed of so-called TE adjectives. TE here means trichotomous evaluative. So typical examples, canonical examples is small, medium and big, other weak, medium, strong, silly, normal, intelligent and so on. So all these are class of TE adjectives, and they can be then modified by hedges. We can distinguish at least three subclasses of these hedges, hedges with narrowing effect, widening effect and specifying effect, so very extremely significantly and so on. Of course there are some other evaluative expressions. Besides others, also fuzzy numbers belong among evaluative linguistic expressions. Then also compound, negative and many other ones. This class is very wide and now forming narrow part of natural language, but the class itself is quite wide, and it is not completely well known which words are evaluative expressions and which are not. I'm speaking about expressions because these are not only words but more complicated expressions. Now, concerning semantics, again, especially about these expressions, any model of the semantics of natural language must capture concepts of context, intension, and extension. First of all, we have to start with concept of possible world. Instead of possible world, I will usually speak about context. Because we will confine only to this class of evaluative linguistic expressions, and here the situation is much simpler than in very generality. The context here is a triple of we can simply confine to real numbers, triple of ordered real numbers, which characterize the, say, smallest reasonable value, largest reasonable value, and some typical central value. For example, distance in the Czech Republic, this can be in kilometers. Smallest value is 10, 100 kilometers, and 400 is the largest, because Czech Republic is a small country. Some like Korea. Korea is also, this would work also for Korea, but this doesn't work for Russia. In Russia, small distance is 100 kilometers, long distance is 3,000 kilometers, and typically medium can be 500 kilometers, and so on. Of course, we have infinitely many possibilities. What is intension? Intension is formalization of a property. It is specific that it is invariant with respect to various contexts, but it is simply we have only one intension, but for concrete specific context it provides different truth values. Again, the same example. For the context for the Czech Republic, 150 kilometers, the truth that it is small, or that it means near, is 0.4. But in Russia it is 0.95. So mathematical model of intension, which is here, say classically, way how it is proposed already by logicians many tens of years ago. Intension is a function from the set of all possible worlds into sets of objects. In our case, this will be a set of fuzzy sets of objects. And then we naturally come to the concept of extension. So extension is, in our case, a fuzzy set of elements determined by this one intension in a given context, or possible world, if you like. And of course it does change when changing the context. It means that for each context we have other extension of the same one intension. So mathematical model of extension is such a fuzzy set, and here is say graphic illustration. Let us consider some context 0, 4 and 10, whatever numbers it is, kilometers or whatever. So in fact the idea is here that we have ordered scale. Here is left bound, right bound, and some middle part, and so everything which is here is small. It can be even very small, extremely small, and so on. Everything which is here on that right part is big. Again, roughly big, very big, extremely big, and so on. And what is around this middle point is medium. So in a mathematical model, this corresponds to fuzzy sets of this shape. So this is fuzzy set related to, or the meaning of small, very small, and so on. We have developed a special formal logical theory within fuzzy type theory, which provides a mathematical model of semantics of evaluative linguistic expressions. And then intension, as I said, it is a function from set of contexts into set of fuzzy sets. So here is again illustration. These are various contexts, and here are the corresponding extensions. And all this is one intension of what does it mean, say, small, for medium, for big. Intermediate quantifiers. Again, we were inspired by a wonderful book by linguist and logician Peterson, Intermediate Quantifiers, Logic, Linguistics, and Aristotle's Semantics. And in general, we can say that quantifiers in natural language are words that precede and modify nouns. They tell us how many and how much. and they specify quantity of specimens in the given domain of discourse. So example of such quantifiers are here: all, most, almost all, few, many, some, no, and so on. For example, most women in the party are well dressed, few students passed exam, and so on. These intermediate quantifiers, you may have noticed that they lay in between classical quantifiers for all and exists. Therefore, they are intermediate, and they form important constituent of class of generalized, which may be possibly fuzzy quantifiers. The main idea for semantics of these intermediate quantifiers is the following: that these are simply classical quantifiers, but taken over small class of elements, and size of this is determined using appropriate evaluative expression. This cannot be done in classical logic because we have no substantiation why and how the range of quantifications should be made smaller. But this can be done in fuzzy type theory or using the means of fuzzy type theory. So in general, the meaning of quantifier bis r a has three parts. As I said, it is in fact in this case classical general quantifier. All elements of Z has property A, but Z is some specific subset of it can be fuzzy set, so specific fuzzy subset of the fuzzy subset B. And this size of this fuzzy subset Z is evaluated by the corresponding evaluative expression. So we can say that size of this subset Z is, for example, very small or very big, extremely big, and so on. And this provides us the general theory of a large class of these intermediate quantifiers. First of all, of course, classical quantifiers are quite easily expressible, but we can also introduce non-classical quantifiers like here: almost all B's are A, few B's are A, most B's are A, and so on and so on. Now this can be extended to simple noun phrases like small house, very high tree, shallow sea, and so on. Because my time is passing quickly, I will not go into the details, only to give you idea that really this can be done and this can be formalized. Here the idea is that nouns represent some objects which we identify with sets of values of some features. So, for example, people can have, here is example of very tall Swedes. So people have a feature of nationality, people have feature of height, of course weight, color of eyes, and so on, many other kinds of features. So here the idea is that these are people, all people. Some of them have property nationality which is to be Swedes, and some of them, of these Swedes, have the property to be very tall. This is various tallness which are evaluated in the concrete extension which is determined for Swedes. In general, Swedes are said to be taller people than, for example, people from South Europe. So here this context will be different for Swedes from people from Italy and so on. So this here we obtain, this represents a fuzzy set of very tall Swedes. In fact, it is extension of Swedes because we have this very tall Swedes is expression of natural language which has intension, and this intention has various extensions in various contexts. I will not analyze it in detail, only to show you that really there is mathematics behind that. This is not only a picture. Similarly, this is very popular Lotfi Zadek sentence: most Swedes are tall. So most Swedes are tall, this is expression of natural language whose extension is truth value. And again, this construction of tall Swedes suites or very tall suites could be is in the same like on previous figure, but here moreover we consider various fuzzy subsets of these tall suites, and we evaluate size of this fuzzy subset, and the size is evaluated by some concrete evaluative expression, very big, concerning size of this fuzzy subset, and then the greatest of them provides us as truth value. So this is computed using formula of this form, and so it is very easy using this technique to model the meaning of expressions like most suites are tall. Again, here is the corresponding formula. It is in formal language, and of course if we take one concrete model, then we can compute concrete numbers. So everything behind this formula can be seen also in terms of numbers. Now a few words about human reasoning. So-called perception-based logical deduction. I will present it on this example. Imagine a typical situation that you are driving a car and you are approaching a traffic intersection, and the green light is on. And when you are approaching this intersection, this green light suddenly switches to red one. And then you are in decision situation which is described using these 4 rules. If the distance is, say, medium or big, then simply don't stop, do nothing and wait. If the distance is small, then you should brake, you should stop. If the distance is very small, then it is dangerous to stop, because you can finish inside traffic intersection, and therefore it's better to push the acceleration pedal and to leave the intersection quickly. If the distance is extremely small, it means that only, say, 2-3 meters, and you see a red light, you simply continue without interruption, because you can pass through the intersection easily. So if you look at these 4 rules, they give you general rules for driver's behavior, and these rules give do hold independently on concrete place, on concrete intersections. So in various intersections, various towns, whether it is Moscow or Daejeon or whatever, various intersections, you still behave in the same way, but in various different contexts. So contexts are changing here. And of course, people are able to follow them in arbitrary signalized intersection. What is also noticeable, that we can distinguish between the rules, but the meaning of each rule is vague. So we have to cope with that in some way. And the way how to cope is perception-based logical deduction. It is in fact a derivation of standard deduction, standard modus ponens rule, but what here is perception. Imagine the situation that you are an observer and you are in some concrete context, which can be, for example, I don't know, in the field, in the countryside, but also in some street and so on. You will see somebody and you can say, this person is far from you in this context. This person is near from you, this person is very near. So this linguistic expression, which is in fact evaluative linguistic expression, is a perception. So notice that I use here the concept of perception. It is not psychological term, it is technical term, and simply saying that perception is the corresponding expression of natural language, which of course has its semantics depending on the concrete context. And then what we obtain is the way how it should behave. We have also implemented this system of perception-based logical deduction, and it works perfectly well. It has very many kinds of applications because it imitates the human way of reasoning in this situation. Moreover, the linguistic description, it means the set of fuzzy linguistic if-then rules, can be learned from data. it effectively utilizes the expert knowledge which can specify directly in natural language, and then it is implemented with respect to the given linguistic context. We have applications, for example, in control, decision making, time series forecasting, and so on. Concerning human reasoning, with these intermediate quantifiers, we can form also generalization of classical Aristotle's syllogisms. We will speak about intermediate syllogisms. So, in general, a syllogism is a triple of formulas in our case, in which C is a conclusion, and it has two premises, major premise 1 and minor premise 2. An intermediate syllogism is in fact obtained from classical syllogism when one or more of these formulas are replaced by some formula which contains intermediate quantifier. And also we can say that syllogism is strongly valid if in a given theory the following formula is provable. Here this is in our case Lukasiewicz conjunction of these two propositions. So there are four figures analogously as in classical Aristotle's syllogisms, figure 1, figure 2, and these figures differ by order of the premises here in this structure. So this is example, some simple example of syllogism of figure 1. Or if all women are well dressed, and we know that most people in the party are women, then we conclude that most people in the party are well dressed. Another example of the second figure, no lazy people pass exam. And we know that most students pass exam. Therefore, we conclude that some students are not lazy people. Two more figures, almost all old people are ill, and we know also that almost all old people have gray hair, and therefore we conclude from these two premises that some people with gray hair are ill. And finally, the fourth figure, most shares with downward trend are from car industry. All shares of car industry are important, and therefore we learn that, or we conclude from these two premises that some important shares have downward trend, and so on. So this is example how human reasoning can be modeled using in this theory. Let me also mention that what we also have done is the model of human reasoning of detective when using natural language expression. It was inspired by one case of famous Lieutenant Columbo series, TV series. I think everybody of you knows, and it works. Though of course formalization of such cases is quite complicated and it requires penetration into the problem. So, to conclude, what we presented is the concept of fuzzy natural logic, and we demonstrated that it should be developed on the basis of higher order fuzzy logic, fuzzy type theory. We also demonstrated how semantics of several classes of expressions of natural language, and also with respect that their semantics is vague, and how to formalize them. In case of human reasoning, we discussed the concept of so-called perception-based logical deduction, also mentioned implications, and introduced the concept of generalized intermediate syllogisms. And also, what I didn't speak about because of time limitation, fuzzy type theory provides really a reasonably working mathematical model of the vagueness phenomenon, and it can very effectively model the phenomenon, so-called Sorites paradox, paradox of heaps, paradox of Falacros, paradox of Boltzmann, and also so-called higher order vagueness. All of these things can be formalized using this fuzzy logic, and all this belongs to the field which I hope will be extended in some future, and this is the field of fuzzy natural logic. So finally, references. Here are a few references concerning only fuzzy natural logic, not the whole thing. So that's all. Thank you very much for your attention.